Swayam Prabha. Digital India. Educated India.
Welcome to the course Analysis of Variance and Design of Experiments. So now from this lecture we are going to begin with a new topic, that is confounding. Well, confounding is not something independent, that is related to the factorial experiment, because whenever we are trying to do this confounding, that is done inside the factorial experiments. And believe me, this is very interesting. And doing the algebra, that is very simple and it is based on strong statistical theories, but the way we try to do it, that is very systematic. So, there is an approach by which you can conduct different types of analysis while confounding. But the first question comes, why confounding, what is confounding and why should I do it, and what is really happening when we are trying to do the confounding. You see, when we are trying to conduct the factorial experiment and whenever we are trying to take the complete factorial experiment, that means inside each block we are trying to use all the treatment combinations. So, definitely you can see that the experimental units, the cost of material, all things will increase. For example, if you are trying to conduct a 2 square factorial experiment, you need only 4 treatment combination, for which you need only 4 plots in a block. But in case if you are trying to go for 2q factorial experiments, then there are 8 treatment combinations, and if you want to have a complete factorial experiment, that means you want to use all the treatment combinations in each of the block, then you need 8 plots in each of the block. And if you try to repeat it say a small r number of times, then you will need 8 into r number of plots, or say 8r number of experimental units. And if you try to increase the order of this factorial experiment, this number will increase very fast, and then the cost of the experimentation requirement of the experimental units, everything will go much higher. Definitely that you cannot afford, because in every experiment there is a given cost, there is a fixed cost, and you have to conduct the experiment within that cost. So, now the only option is this, we would like to reduce the block size. So, now the question is how to do it, but you can always ask me that we already did when we considered the incomplete block design, that is the same thing we had talked about, and through incomplete block design analysis also you have reduced the block size. So, similarly this confounding is also an alternative approach to reduce the block size, but that is done in a systematic way following the rules of statistics. So, what really happens means, I can tell you in simple language, when you are trying to confound one effect, that means the block size become half. So, in case if you try to say confound one effect in 2q factorial experiment, then the block size will become 4 from 8. And in case if you try to confound here 2 effects, then the block size will become once again half, that is 1/4 of the total block size. So, this is how we try to reduce the block size, and ultimately the cost of experimentations also become lower. So, now we try to understand how are we going to do it and what is really happening, that is more important to understand, that whenever we are trying to confound a factor, what is really happening and how we can understand it using the tools of statistics. So, that is what we are trying to now do in this lecture. So, in this lecture, in order to understand the basic concepts, I am simply going to take the setup of 2 square factorial experiment, and I will try to show you each and everything. Once you get convinced, after that doing further analysis is very simple. So, let us begin our lecture. Okay, so now in this lecture, first we have to understand that why do we need the confounding. So, in case if the number of factors or levels increase in a factorial experiment, then the number of treatment combination increase rapidly. And when the number of treatments combination is large, then it may be difficult to get the blocks of sufficiently large size to accommodate all the treatment combination. This is exactly what we have just talked about. So, under such situations, one may use either the connected incomplete block design like as balanced incomplete block designs, say for example BIBD, and where all the main effects and interaction contrast can be estimated. Or the second alternative is that we can use the unconnected designs where not all the contrast can be estimated. You remember the definition of connected design? In this design all the elementary contrasts were estimable. So, now we are trying to say okay, we do not want to estimate all the elementary contrasts, but some of the say contrasts may not be estimable, and this is going to help us in reducing the block size. So, now if you try to see here, non-estimable contrasts are called as confounded. Now, if you try to recall that in the beginning of the course at one point of time I had told you that I will be using the word non-estimable function, and I will give you a hint at that time that that why are we going to use it. So, if you try to recall that lecture, I had given you this definition in the beginning of the course, but now we are going to implement it, that non-estimable contrasts are said to be confounded. But the question here is how they are non-estimable, why can't you estimate them on, and what are you trying to do here so that these contrasts are non-estimable, and how it is going to reduce the block size. So, do you recall that a linear function say lambda transpose beta is said to be estimable if there exists a linear function L transpose y of the observations on the random variable y such that expected value of L transpose y is equal to lambda transpose beta. So, now there are two important questions which come here. What is the confounding? What is this confounding? What is the meaning of this confounding? And secondly, how does it compare to the balanced incomplete block design? For example, if you want to reduce the block size and if you try to use the confounding as well as the balanced incomplete block design, what is the difference between the two and what is going to happen and how it compares to that. So, we try to consider here first that what is confounding, and in order to understand it we consider here a very simple setup of 2 square factorial experiment which has two factors capital A and capital B. So, now as we know that there are going to be here 4 treatment combination which are indicated by here 1 A B and A B, and suppose each batch of the raw material to be used in the experiment is enough only for 2 treatment combination to be tested in a block, right. For example, if you want to go here for the complete factorial, you will need here 4 plots in which you will try to give here 1 A B and A B all the 4 treatment combination. But suppose you do not have that much of experimental material which can be used for the 4 plot, but it is only for say out of you have only material only for 2 blocks. So, definitely you want to give here this 2 out of this 4 treatments, and then I mean the remaining 2 will go to another block. So, now the question here is how are you going to choose 2 treatment out of the 4 treatments, right. So, we know that now only 2 batches of raw material are required, thus 2 out of the 4 treatment combination must be assigned to each of the block which has only now 2 plots, right. So, now suppose we are trying to conduct this factorial experiment inside a randomized block design. So, in that case we try to write down here the model and then we try to understand what is the meaning of this confounding. So, now if you try to write down here the model, this is here expected value of y I j is equal to mu plus beta I plus cow j, I goes from here 1 to 2, that means there are here 2 blocks with the parameters beta 1 and beta 2, and there are here 4 treatments, tau 1, tau 2, tau 3, tau 4, and they are like 1, A, B and AB. So, now you already have understood that how do you write the these here main effects and interaction effects. So, this is what I have written here. So, this we already have understood in the case of factorial experiment how to obtain them, and then we are trying to write down here the treatment totals due to this by this square brackets and divided by the total number of observations, right. So, this is how we can find out the main effect and interaction effect. Now, we have to choose out of these 4 treatment combination 1, A, B and AB, I have to choose here 2 treatment combinations, so that I can allocate them to each of the 2 block. Suppose out of these 4 I try to choose here say 1 and AB in say block number 1, and the remaining 2 A and B in the block number 2. So, block number 1 will have the effect beta 1 and block number 2 will have the effect beta 2. Now, we try to compute the average response corresponding to this treatment combination 1 A, B and A, B. So, now you can see here this 1 is appearing here. So, the response due to 1, that is I am trying to indicate here as a y and inside the parenthesis 1. So, the model will be expected value of this y 1 is equal to mu plus beta. Which beta? Out of beta 1 and beta 2, this is appearing in the first block. So, we have here beta 1, and then the treatment corresponding to 1 I am indicating here by say tau 1, right. Similarly, if you try to see here, what about this here AB? This AB is again appearing in the block number 1. So, I can write down the model that expected value of y corresponding to this AB as mu plus beta 1, because it is appearing in the block number 1, and the treatment combination corresponding to AB. So, this is how I am trying to indicate it. So, this is indicating that treatment effect due to the treatment combination AB. That is only a symbolic representation, so that I can explain you in a very clear way, right. Similarly, if you now come to block number here 2. So, block number 2 you can see here you have here A. So, now you can write down the model for the response for this A here as a expected value of y A is equal to mu plus now beta 2, because that is appearing in the second block plus the treatment effect due to A. And similarly, if you try to look at here the fourth one, this is here B. So, B is appearing in the fourth place, which is happening here like this, and you can write the response here as the expected value of y B, which is equal to mu plus here beta 2, because this is appearing in the block number 2. So, this has the effect of that second block, plus here the treatment effect due to the effect B, right. So, now we have written here the models for the observations for each of the treatment combination under the set of randomized block design. Now, well, you can see here one thing that just in order to make the this understanding simple, I am not considering here the factor here 1 upon 2r, because I will have to indicate it again and again, and at the end that is going to remain as such. So, at this moment I want to show you the meaning of confounding, that how it is appearing through the setup of randomized block design model which we are considering. So, what we try to do here, that we try to write down here the A. So, if you try to recall that you have written here 1 upon 2r into AB plus A minus B minus 1. So, this I am trying to ignoring. I am trying to ignore this 1 upon 2r, because that is going to remain in all the this factor. So, I just want to make the illustration simple. And now, what is the meaning of this AB? This is your here y AB, this is what is here A, this is here y A, this is your here B, which is here y B, and this here is 1, here is y 1. So, now I try to write down these expected value of this y A B, y A, y B and y 1 using these symbols. right. So, I try to write down here like this. So, I try to write down here like this, means expected value of the y corresponding to the treatment combination AB plus expected value of y corresponding to the treatment combination A, expected value of y corresponding to the treatment combination B, and expected value of y corresponding to the treatment combination 1. So, now if you try to see here what is happening, in this case this mu, mu, mu and here mu, that is getting cancelled out without any problem. And if you try to see here, what about this here beta 1 and beta 2, this beta 1 is getting cancelled here by this beta 1, and this beta 2 is getting cancelled here with this beta 2, and we have here finally tau A B plus tau A minus tau B minus tau 1. So, you can see here there is no block effect present in this structure. So, the block effect is not mixed up with the treatment effects. So, we see here that in this case the main effect A is not confounded, right. And now, the same thing I try to do for the factor B. So, that we can write down here, say expected value of y corresponding to treatment combination AB plus expected value of y corresponding to the treatment combination B, then expected value of here y corresponding to the treatment combination A, and expected value of here y corresponding to the treatment combination 1. Now, in this case also you can see here this mu, 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 this is getting cancelled out, no issue. And similarly, if you try to see here that this beta 1 and this beta 1, they are getting cancelled out, and this beta 2 and this beta 2, they are getting cancelled out. So, finally, we have here tau A B plus tau B minus tau A minus tau 1, and here also you can see that all the block effects, they are getting cancelled out. So, there is no block effects. So, we can say that here B is not confounded, no issues. Now, we try to consider here this A B. So, in the same way we write about A B. So, you can see here this is expected value of y for the treatment combination A B plus expected value of y corresponding to the treatment combination 1 plus expected value of y corresponding to the treatment combination A plus expected value of y corresponding to the treatment combination B. Now, you see what is happening in this case. Anyway, this mu, 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 mu get cancels out. But in this case you can see that beta 1 and beta 2, they are not getting cancelled out. This is here plus beta 1 and this is here plus beta 1. So, they are appearing here as say twice of beta 1, and then we have here beta 2 which is happening here minus beta 2 and here minus beta 2. So, this is happening here minus of twice of beta 2, right. And then here this tau A B, tau 1, tau A, tau B, they are also appearing here. So, now can you see the difference here? Now, if you try to look back, when you were trying to write down here A, there was no effect of beta 1, beta 2. When you were trying to write about this B, there was no effect of beta 1 and beta 2, actually they were cancelled, and but in the case of AB, there is an effect of beta 1 and beta 2. So, now you can see here that in this case the block effects are mixed up with the treatment effects. So, the block effect beta 1 and beta 2 here, they are mixed up with the treatment effects and we cannot separate them out, right. So, this means in this case whatever the value of A B we are going to get, that is going to contain the effect of blocks as well as treatments. On the other hand, when you are trying to get the value of B from here and value of A from here, they were having only the effect of treatment combination. So, they had only one effect, that is effect due to the treatments, but in this A B the values will have block effects as well as the treatment effects, and both these effects are mixed up with each other. And it is something like this. If you try to take a very simple example in your life, that suppose I take some salt and I take some grounded sugar, and if I try to mix it together, then looking at the powder, that is simply going to look as white powder. And can you really separate them? But in case if I try to mix up with our, see here some grains of wheat with the grains of rice, we can easily separate them out. So that is what is happening now when we are trying to estimate here AB. This value is going to be a single value, but this has both the effect, the block effects as well as the treatment effects, and we cannot separate them out. So that is why this is called as confounded. But now if you try to see what is really happening in the earlier two cases, this block effect was not appearing. Why? Because the beta 1s and beta 2, they were getting cancelled out. But in this case, the beta 1 and beta 2, they are not getting cancelled out. This means what? If you try to see, when you are trying to find out the values of A, B, or say capital AB, they are simply based on the allocation of treatments in different blocks. And when you started, you had 4 treatments, you have to choose only 2 treatments which you are going to assign in that block. And if you try to see who told you to assign those particular treatments to a block 1 and say another treatments to block 2, that was your own decision. That means it matters that the way you are trying to choose those 2 treatments such that they are appearing in the block, that is going to make a difference. And the difference is that in this case, the way you have assigned these 2 treatments to these blocks, the interaction effect AB is getting confounded. You cannot estimate it. So the moral of the story is that it is your choice, or it is the choice of the experimenter, that which of the effect has to be confounded. Now, if you try to think in the opposite way, I will say, well, if I want to confound the effect AB, then I am going to choose this treatment allocation. The way we have assigned here the treatment to the 2 blocks, I will follow that treatment allocation. I will try to conduct my experiment. So AB is not estimable, but at least my block size has become from 4 to 2. So this is the meaning of confounding. But now we will try to understand it more. Right. So now if you try to see here that in case if you try to choose other arrangement of the treatments in the block, suppose if I try to take here say here treatment number here 1 and AB in block 1 and A and B in the block 2, and if you try to do the same exercise which I have just shown you, you can find out that in this case A is getting confounded, and you can write here A using the same method, but you will see here that now A is getting confounded because this block effects and treatment effect, they are appearing here together, right. So, in this case the main effect A is getting confounded if you are trying to arrange the same 4 treatment in the 2 blocks in this particular way, and in case if you try to use this approach, then the interaction effect AB is getting confounded. So, that means it is in your control, or it is in the control of the experimenter, that based on the decision the different treatments can be allocated to the different blocks. So, first it has to be decided that which effect is to be confounded, and then we have to decide that which of the treatments are going to be allotted to any block. Yes, within the block, means if you want to assign here A and B, then whether you are trying to assign A in the plot number 1 and B in the plot number 2, or you are trying to assign it like here means B to the plot number 1 and A to the plot number 2, that is decided randomly. So, the order in which the treatments are run in a block, that is decided randomly. And the choice of the block to be run first, whether you want to use the block 1 first or the block 2 first, that is decided also randomly, because that is not going to make any difference on the confounded effects. So, out of this discussion now we can observe that for a given effect, when two treatment combination with the same signs are assigned to one block and the other two treatment combination with the same but opposite signs are assigned to another block, then the effect gets confounded. Now, how does it came? Means how suddenly from this discussion this observation cropped up? Try to see what are we trying to do, and I will come back to the same statement. Now, try to see when you confounded AB. Now, I can use this terminology that you are the one who has taken the decision to confound AB. Then what you have done? You have assigned AB and 1 in the block number 1 and A and B in the block number 2, right. And in case if you try to see here, what is here AB? So, AB in case if you try to write down here, this was here 1 upon 2 r A minus 1 into B minus 1. So, this is going to be here like this 1 upon 2 r A B minus A minus B plus 1, right. So, you can see here there are two terms which are appearing here with the plus sign, which is your here this plus 1 and AB. They are appearing with the positive sign. So, you are trying to assign the two effects with the positive sign in the one block and the remaining two effects which are appearing here with the negative sign. You can see here A is appearing as minus A and B is appearing here as say minus B, that is going into the block number 2. So, you can see here like this. So, now when you are trying to assign the treatment combination with the same signs in one block and the remaining treatment with the opposite signs in another block, then that effect is getting confounded. Now, can you see why this is happening? You are trying to say that your AB is obtained here like this, but out of this 4 treatment 1 A B A B, those treatment combinations which are appearing here with the positive sign, you are trying to assign them in the block number 1, and those treatment combinations which are appearing here with the negative sign, you are trying to assign them into block number 2, and then the interaction effect AB is getting confounded. That is what you are observing. And same thing if you try to see here, when you had done for the A, then A can be written here as say 1 upon 2 r A minus 1 into B plus 1. So, this is going to be here 1 upon 2 r A B plus A minus B minus 1. So, here this A B and A, they are appearing with here positive sign, you are trying to assign them in the block number 1, and then this B and 1, they are appearing here with the negative sign, you are trying to assign them to the block number 2. So, once again you are trying to do it the same thing, that now I can say that in case if you want to confound A, try to write down here A in this way in terms of the treatment combination, and try to assign all the treatment effects which are appearing with the same signs in one block and with the opposite sign in another block. So, that is what we have done, and that is what I have written here, that for a given effect, when two treatment combination with the same signs are assigned to one block and the other two treatment combination with the same but opposite signs are assigned to another block, then the effects get confounded. But now this is happening, yes, we all agree that this phenomena is working, but can you tell me why this is happening? Right, here in this case if you try to see, this A is not getting confounded. Why? Because if you try to see here, if you try to write down here this A here as say 1 upon say here 2R, and this will become here A minus 1 into B plus 1. So, this is going to be here 1 over 2R A B plus A minus B minus 1. Now, you can see here what is happening. If you try to take here A B and here 1, one is appearing with plus sign, another is appearing with minus sign, you are assigning it here in the block number 1, and this A and B, they are appearing with plus and minus sign, they are assigned in the block number 2 with respect to A. But now in this case A is not getting confounded, but only AB is getting confounded. Why? Can you think about it? Yes, you have learned that a linear parametric function is going to be estimable only when it is expressed in the form of a linear contrast. And if you try to see, when you are trying to consider here this AB and then you are trying to assign here 1 and AB, both are appearing here with the positive signs and they are not making here an elementary contrast, or in general, since all the treatment combination with the positive signs, they are appearing in the block number 1. So, they are not trying to frame the linear contrast in AB. And same thing is happening here with respect to here B, block number 2, that you are trying to assign here two treatment combination A and B, which are appearing in the factor AB with here the same signs minus minus. So, they are not forming the elementary contrast within the block. So, that is why when you are trying to assign this 4 treatment combination according to the signs of this AB, then they are getting confounded. But on the other hand, if you try to observe with respect to here A, what is happening here? This you are trying to assign here 1 and AB. They are appearing here in A as here like this minus 1 and AB. So, they are trying to form here an elementary contrast. And in block 2 also A and B, they are appearing here with plus and minus signs. So, within the block with respect to capital A, the treatment combinations are trying to form here an elementary contrast. So, that is why they are estimable, because if you try to see here that when we are trying to write down here this here you can see this AB or AB here, you can see here now in this case they are in the form of a contrast, and there are here elementary contrast. For example, this AB can be written here as AB minus A and plus here 1 minus here B. So, if you try to see here both of them, they are the elementary contrast, and this is happening with all A, B, and this will happen in general with other factors also without any problem. So, now that is the reason, and the same reason follows here in the case of here A, when you are trying to assign A and AB to the same block, then they are not forming the elementary contrast within the block, and that is why they are getting confounded, whereas if you try to write down here A B or here B, they will not be confounded. So, this is in your hand how you want to confound a particular effect, but now the rule is very simple. Whatever main effect or interaction effect, whatever effect you want to confound, just try to write down in the form of a linear contrast and try to assign all the treatment combination with the same sign to one block and all the treatment combination with the opposite sign to another block. That is all. So, now you can see here the entire story is now clear, that why confounding is coming and how it is making a particular main effect or the interaction effect to be non-estimable. Right. So, the reason behind the observation is that every block has treatment combination in the form of linear contrast, then the effects are estimable and thus not confounded. And this is also evident from the theory of linear estimation that a linear parametric function is estimable if it is in the form of linear contrast, that we had discussed in the beginning of the course after a couple of lectures only. Right. So, the contrasts which are not estimable, they are said to be confounded with the difference between the blocks, which is the correct statement, that just by saying confounding or the effect is confounded, that does not make any sense, because confounded with what? So, if you try to see here, means in this case when you are trying to write down here, you have written here A B, where you have here this factor as beta 1 minus beta 2, and the same thing here in the A also here, this is beta 1 minus beta 2. So, there is a difference between the blocks or the block effects. Right. So, the effect which is not estimable, that is confounded, but the correct statement will be confounded with the difference between the block effects. But usually you will say that people try to use only one word here, that the effect is confounded. So, but you have to be clear that what is the meaning of this statement. Right. And those contrasts which are estimable are said to be unconfounded with block, or they are free from the block effect, that we have now seen. So, now in case you try to address here the answer of the second question, then let us see that if your objective is simply to reduce the block size, and if you have here two options, that you can use here the balanced incomplete block design, or you can use the factorial experiment, then how does it compare together? But one thing you have to keep in mind, these are two different concepts. Right. In my personal opinion, they are not really comparable, because BIBD is used under a different type of setup, and this factorial experiment is used under a different type of setup. Both are based on different types of concept, but still just for the sake of understanding, we try to consider it here. Right. So, in order to compare them, let me try to take here a very simple example. And we try to consider here a 2q factorial experiment in which the block size is going to be 8, and then we try to compare it with a similar type of setup in the BIBD, where the block size is also 8. Right. So, suppose the raw material available to conduct the experiment is sufficient only for a block of size 4. So, that means in the 2q factorial experiment you have to confound one effect. So, the block size will become 4. So, now instead of the confounding, suppose we decide to use the balanced incomplete block design. So, in this case, as you know that we have to choose the parameter in a particular way, such that those conditions are satisfied, like as B k is equal to V r, lambda V minus 1 is equal to R into A minus 1, and B is greater than or equal to V. And beside those things, you have to assure that such a BIBD always exists. So, what we try to do here, that we try to choose here these parameters: B is equal to 14, K is equal to 4, V is equal to 8, R is equal to 7, lambda is equal to 3. B is the number of blocks, K is the number of plots, V is the number of treatments, R is the number of replicates, and lambda is the number of times a pair of treatment occurs in blocks. So, now do you remember that we had derived the efficiency factor E, which was lambda V upon K R, and in this case this will come out to be here 6 upon 8, or say 3 upon 4. Now, we had obtained, if you remember, the variance of an elementary contrast of the estimates of the treatment effects. So, if you recall, we had obtained this expression when we had talked about the BIBD, and the variance of tau j tilde minus tau j prime tilde under BIBD came out to be 2k upon lambda V into sigma square. So, this will come out to be here 2 upon 6 sigma square, or say 1 upon 3 sigma square, right, when j is not equal to j prime. Now, we try to do the same thing under the factorial experiment. So, we try to consider here an unconnected design in which 7 out of the 14 blocks are getting the treatment combination in the block 1, here say A, B, C and A, B, C, and the remaining are getting here the treatment combinations 1, A, B, B, C and A, C. And if you try to see, I simply want here that one factor has to be confounded. Right. So, we will talk about it. Usually what we try to that because the higher order interactions are difficult to interpret. So, we try to choose here ABC and then we try to assign these treatment combinations accordingly. So, if you see here I am writing here ABC as A minus 1 into B minus 1 into C minus 1 and then whatever the treatment combinations they are appearing here with the plus sign I am trying to put them here in the block number 1 and whatever the treatment signs which are appearing with the negative signs I am trying to put them into the block number 2. So, that this ABC is not estimable, right. Okay. Now, you can recall that we had found the variance of tau j hat minus tau j prime hat in the case of randomized block design and which was 2 sigma square upon r. So, this will come out here 2 upon 7 into sigma square for j is not equal to j prime. So, there are here 4 linear contrasts. So, the total variance is going to be 4 into this twice of sigma square into 7. So, we have here the factor of here 8 sigma square upon 7. And if you try to see here, this is here the variance of this thing. And if you try to see here, this is smaller than the variance under BIBD. So, we observe that that at the cost of not being able to estimate ABC, we have better estimates of A, B, C, AB, BC and AC, and ABC is not estimable, that cannot be estimated with the same number of replicates as in the case of BIBD, right. But still I would say here that yeah, it is not really means comparable in my personal opinion, and this example I have taken only for the sake of understanding, nothing more than that, right, because the concept behind the incomplete block design and confounding they are different, and in fact you can use actually both. You can use the confounding inside the incomplete block design also. Well, we are not going to talk about it here, but you can do it, right. So, now one question comes here that when you are trying to confound an effect, now you have understood that is your choice, that is the decision of the experimenter. So, which of the effects to be confounded? So, now we decide only on one factor, that because you see when you are trying to consider some higher order factorial experiment, then you are going to get their higher order interaction effects also. So, when you are trying to consider them, the higher order interactions are difficult to interpret and they may not also be usually large. So, then we try to take a call that well, they are not going to contribute much. So, it is better to confound them, and then in turn it comes out to be that it is a better option to use the confounding arrangement which provides better estimates of the interaction in which we are more interested. So, we always try to take a call that higher order interactions are getting confounded. But now we try to see here what really happens when we are trying to confound the higher order interactions, right. You will see that when we are trying to do so, some other main effect or the interaction effect, they also gets confounded automatically. So, now let us try to see here how this is happening. So, but before that we have a definition of what is called a confounding arrangement. So, the arrangement of treatment combinations in different blocks whereby some predetermined effects, either main or the interaction effects in the form of contrast are confounded, is called a confounding arrangement. So, that is a very simple thing, right. For example, you have just seen here in this case that how you have chosen the 4 treatment combinations out of 8 treatment combination A, B, C, A, B, B, C, A, C, A, B, C and 1, that which of the treatment combination are to be assigned in the block number 1 and block number 2, such that ABC gets confounded, right. So, this arrangement is called as confounding arrangement. For example, you can see here that now this is the same arrangement which I just shown you, that if you want to confound the ABC in the 2q factorial experiment, then you need to choose these 4 treatment combination ABC and ABC in one block, one AB, BC and AC in another block. So, this is called confounding arrangement, that is the simple terminology, right. And when we are trying to replicate these blocks, for example, you have this here 2 blocks, say here block number 1 and say here block number 2, and if you try to repeat them say r times, right. So, with the treatments of each set being assigned to the same block and each of these sets being replicated the same number of times in the experiment, we say that we have a confounding arrangement of 2q factorials in 2 blocks. Right, definitely you are going to use the basic principle of replication. We have not considered in the when we took the example of 2 square factorial experiment with irrigation and nitrogen, because we wanted to understand what is happening. But now you have understood that what is really happening in the factorial experiment, how are you going to conduct the this confounding. So, now definitely you have to use the principle of randomization, replication and local control if you want to have a good design, right. Now, one thing what you have to see here, that when you are trying to say that the effect that you are going to confound, they are not going to be estimable. So, the first question comes here, you have to take a call that in the given factorial experiment, which of the effects you want to confound. And this is a good practice, that when you are trying to conduct the confounding arrangement, you try to confound only those effects which you want, right. But you will see that when you are trying to choose some of the factors to be confounded, then some other factors will also be getting confounded automatically. So, now we try to understand what really happens when we are trying to confound the effects in different blocks, right. So, it may be noted that any confounding arrangement has to be such that only predetermined interactions are confounded, and the estimates of the interaction which are not confounded are orthogonal whenever the interactions are orthogonal. So, now we have here a definition that the interaction which are confounded, they are called as defining contrast of the confounding arrangement. For example, in the earlier case you have confounded ABC. So, ABC is the defining contrast in this case, right. Now, you can see here ABC is the defining contrast, right. So, and now I can say that a confounded contrast will have treatment combination with the same signs in each block of the confounding arrangement. For example, if you want to look at AB, because in the case of a 2q factorial experiment, then the AB can be obtained from A minus 1 into B minus 1 into C plus 1 here some divisor will be there, which I am just ignoring for a while, right. Suppose if you want this AB to be confounded, so you simply try to open it, try to see the which are the 4 terms which are appearing with the positive signs, which will come out to be here 1, A, B, C and A, B, C. You try to assign them in block number 1, and the other remaining 4 treatment combination which are here A, B, A, C and B, C, try to assign them into another block which are appearing with the negative sign. So, you can see here means if you want to have a complete factorial experiment, then in the case of 2q factorial experiment you will have a block size of 8 plots, but now when you are trying to confound here one factor, the block size is becoming half, that is 4, right. So, now suppose if I take a situation where you want to say that okay, I want to reduce the block size more. So, for example, in case if I take an example of this 2q factorial experiment, where you have seen that when you are trying to confound one factor, then the block size is becoming 4. Now, suppose you want to make it 2. Suppose your experimental material is sufficient only for a block size of 2 plots. So, now that means we need to confound here one more factor. So, suppose we take here an example that along with ABC, we want to confound one more factor here, C also. So, now what we will try to do here, that you try to look into the table. Do you remember you had created a table of here 1, A, B, A, B, C and so on, which with here plus and minus sign for all those things. Best thing is to look at into that table, try to keep that table aside with you and try to see that which are the common positive and negative signs between A, B, C and C. And try to just to see that whatsoever are the same signs, try to assign them into one block, and whatsoever treatment they are with the opposite sign, try to assign them into different blocks. So, in case if you try to do it, so if you remember, this is the block when you are trying to confound the ABC. Suppose this is here block 1 and this is here block 2, right. Now, you try to look into the row of factor C and try to see in the rows of A, B, C and C which are the factors which have got here plus sign, and try to assign them into blocks, say blocks 1 and blocks 2, and those appearing with the negative sign you try to assign them to block, means another 2 blocks. So, if you try to do so, you will get here this A and B into here one block, C and ABC into another block, and from the block number 2 you can further divide them into 1 and AB into the block number 6 in the first block, and BC and AC in the second block here. So, now you can see here when you are trying to confound here one more factor C, then the block size is now becoming here 2, and those 8 treatment combinations have been divided into 4 blocks, and each of the block has 2 plots in which you have to conduct the experiment, that you try to give here A and B, then in another block C and ABC, then you try to give 1 and AB in the third block and BC and AC in the fourth block. Right. So, these blocks of the 4 treatments now are divided into 2 blocks with each having 2 treatments, and they are obtained in this particular way, right. Now, I will try to show you. So, now if you try to look into the row of here C and then try to assign, means all the positive treatment combinations of C in one block and with the negative signs in say another block, and now you try to see here what I told you. I am just trying to illustrate it here. So, now you try to look into the blocks with the positive signs in this ABC, which is here ABC and ABC, and follow the positive sign in the factor here C, and then try to see which of the treatment combinations in this expansion they are appearing with plus signs. So, these are here C, AB, AC, ABC, and then right, and then try to see that which of them are here common. So, you can see here that C and ABC they are here common. So, C and ABC goes into one block and other treatment combination into different blocks. So, we try to identify the treatment combination having the common signs, means signs in the minus signs in the 2 blocks in 1 and 2, and these treatment combinations are C and ABC. So, assign them into one block, and the remaining treatment combinations out of those ABC and ABC are A and B, which go into another block, right. So, you can see here means C and ABC you have given it in one block. So, now this AB will go into another block, and similarly in the from the block number 2 here you assign C and ABC into one block. So, this AB and AC will go into another block. So, this is what exactly I was trying to tell you, Right. So, and if you try to see here that if you try to do this exercise at the end, you have here these 4 blocks in which A, B, C and C both are confounded, right. But if you try to observe here one thing, that when you are trying to make such assignment of treatment combination into these 4 different blocks, each of size 2, we notice that another interaction effect AB is also getting confounded automatically. So, what we observe here that when we are trying to confound 2 factor, a third factor is also getting confounded automatically, and this situation is quite general. So, now we need to understand more that how we are going to handle such situations. Right. So, okay. So, now we stop in this lecture and we have come to a point where we can see that when we are trying to do something, something else is automatically happening. So, that is the point which we have to take care. But in this case, I was able to show you using this simple example, but definitely when you are trying to take a higher order factorial experiments, you cannot really go into these types of details, but you need a scientific way, a statistical way by which you can obtain these block arrangements. Block arrangement means how these different treatment combinations are going to be assigned to different blocks. So, how to go, do it? This I will try to discuss in the next lecture, but it is very important for you that you try to understand the concepts the way we have developed it. This is going to give you a sort of fundamental understanding that in the next lecture when I try to show you that how you are going to work in a systematic way, mechanical way that looks mechanical, but behind that rule there is some mechanics which is based on the statistical laws. So, this is very important for you to understand what is really happening and why this is happening. So, you try to revise this lecture and I will explain you more concept in the next lecture. Till then, goodbye.